Raptor is a rapid reconnaissance UAV for operators in the field. The aircraft uses inexpensive components for deployment in high-risk environments. In order to be an effective asset to the user, the aircraft was designed to achieve a range of 30 km with a cruise speed of 80 meters per second. To reach these cruise speeds, the high thrust-to-weight ratio of a turbojet engine was required. The selected unit is capable of producing 100 newtons of thrust. To gather more information about in-flight performance, a strain-gauge engine mount was designed to measure thrust, and from thrust, drag. The engine was placed above the fuselage to allow the strain gauge unobstructed deflection. This led to a VTOL configuration to allow the jet wash to pass freely between the tail surfaces. To maintain strength and stiffness at the design speeds, glass fiber layup was added to the typical wing structure design that uses foam wings and carbon spars. To validate the baseline performance of the aircraft, a prototype version was designed with a low-risk electric ducted fan propulsion system. Due to the low thrust of the EDF, a bungee system was used to get the aircraft up to takeoff speed. Flight testing of the prototype aircraft successfully provided in-flight thrust data and validation of the aerodynamic design. In straight-level flight, the drag coefficient was measured to be within 4% of the closest wind tunnel value. Following the lessons learned from the successful flights of the EDF aircraft, final design modifications were made. To maintain the correct center of gravity with the heavier turbojet engine, the fuselage of the aircraft was extended forward. Due to the increased forward area and pitching moment from the engine, the tail area was increased to provide sufficient control authority. Landing gear was added to allow for a controlled ground run and improved launch abort options due to the complexity of the jet engine. Access to the fuel valves and electronics was greatly improved with the implementation of a split fuselage section. The ability to quickly recharge batteries and refuel the aircraft maximized the number of test flights achieved. The jet engine, fuel system, and landing gear were subjected to taxi testing to ensure successful operation prior to flight testing. During final flight testing, the aircraft initially showed some unfavorable flight characteristics, which were improved by adjusting aileron positions, control input settings, and the center of gravity. Following these modifications, the aircraft performed well. The aircraft provided thrust and drag data, measuring the drag coefficient to be within 4% of the closest wind tunnel value. During the test flight, the aircraft achieved speeds of 59 meters per second and covered an approximate distance of 12.5 kilometers on a single tank of fuel. These flight tests demonstrated the capability of the aircraft to fulfill its role and highlighted potential areas of improvement for the future.